Hello. Um, this is Prof. Nanius, and I'm going to explain a little bit of the basics of the Wronskian, why it matters, what the results say, um, how you can use the results, and to explain why the Wronskian does what we say it does. So let's get started with the math. Okay. All right, here we go. I want to make sure I am indeed screen sharing, and I am. So the Wronskian and linear differential equations. Now, first of all, what is it? And I know that now I'm going to be working with two functions. Higher dimensions follow similarly. But if you have a function, let's say f and g, and the functions are differentiable, and let's say it's going to be differentiable on some interval, including, 0. I'm not going to be too picky about this in this talk. Then the Wronskian is going to be the determinant of the Wronskian matrix, where in the first row you have an f and a g. In the second row you have the derivatives. But the determinant you calculate for a 2 by 2 by multiplying these things like so. So that's going to be, so basically the Wronskian inputs two functions and outputs two functions. Now, just a little bit of terminology. Uh, if this is the terminology will be about linear independence. And basically, if we have functions f1, f2, f3, all the way out to fk, some finite number of functions, we say that these functions all the way out to fk are linearly independent. I'll abbreviate by Li. If given constants or scalars, alpha 1, alpha 2, all the way out to alpha k, and we have the following sum, alpha 2, f2, plus alpha 3, f3, all the way out to alpha k, fk. And if this is actually equal to the zero function, in other words, not just zero for some point, but if the sum of these functions add to zero as a function, then all L1, L2, all the way out to LK, mean alpha K must be zero. Now, that if you haven't had linear algebra before, that might be a mouthful, but here's what it really means. This really means none of the functions on the list can be written as a linear combination. So linear means adding functions plus scalars of the remaining functions. Now, a very, very quick example to see what I mean, just so you get a feel for it. So let's look at three functions. So for example, one, suppose we have the function sine squared x, cosine squared x, and then we have the constant function 1. Well, these are not linearly independent because, as you know, sine squared x plus cosine squared x is equal to 1. So those are not linearly independent. Okay, that's or another case. Let's say you have x squared. Let's say you have x squared plus x. Then you have the third function x. Well, these are not linearly independent because you can get the middle function by adding this function to that function. So those are examples of things that are not linearly independent. So the question is, why do we care? Well, and I'm going to stick with the type of differential equation that is most often studied in the first course. Well, if we have a differential equation, linear differential equation, second order with constant coefficients, so we have something like this, y double prime plus a1y prime plus a2y, and we'll make it homogeneous, meaning equal to 0. Well, it's a mathematical fact. Like if for a second order linear differential equation with constant coefficients, that all solutions can be written as a linear combination of two linearly independent functions. So let's just look at a practical example. For example, if we have y double prime plus y equals 0, you can check that y1 equals cosine of x, y2 equals sine of x. You can check that these are both solutions. Now, if we could show that cosine of x and sine of x are linearly independent, then we know from the theorem that all solutions are of the form a cosine x plus b sine x. So every single solution to that differential equation will be a combination of those two by a theorem, which I'm not proving here. So we would like a good way to show that these things are linearly independent. Okay? Or let's look at a second example. So we have a second example. Let's say we have y double prime plus 3y prime plus 2y equals 0. You can check that y1 equals e to the minus 2x, y2 equals e to the minus x are solutions. Okay, and notice the characteristic equation would be m squared plus 3m plus 2, have roots -2 and -1. That's not germane to this, but so if we could show that e to the minus 2x and e to the minus x are linearly independent, we would therefore know that all solutions are of the form C1 e to the minus 2x plus C2 e to the minus x. Now, I'm doing this for constant coefficients, but if you have a differentiable function in front of the y prime, differential function of x, and a differential function of x in front of y, what I'm saying here would also work. I'm insisting that the coefficient in front of the y double prime be constant, a non-zero constant. Okay. Now, so that's why. So let's save this. Let's just say step 20, 25, 3. Come on. All right. Save that. Now let's get a new one. So, okay, so we know that. That's y. So, what does a Wronskian have to do with this? Well, the first fact one, if the Wronskian of two differentiable functions, y1 and y2, is not identically zero, as this means is not zero for every single value of x on some interval, let's say a b, where a and b could be in positive and negative infinity. So if we have a non-zero Wronskian, well, let me rephrase it this way. I'll put it like this. I'll do it like this here. What I want to show, I didn't want that. Come on. All right, here we go. I want to say that y1, y2 being differentiable functions over this thing are linearly independent if and only if the Wronskian is non-zero over this interval here, over some interval. And let's see why this is the case. Well, of course, let's say y1 and y2 are not linearly independent. Then this means that y1 can be some scalar multiple of y2, because that's the only way that can happen when you have two functions. Then if you compute the Wronskian, which is the determinant of y1, y2, y1 prime, y2 prime, that's going to be the determinant of k, y2, y2. The derivative is k, y2 prime, y2 prime. What we get out of here is k, y2, y2 prime minus y2 times k, y2 prime, and that's clearly zero. So we see that if the functions are not linearly independent, then the Wronskian is in fact identically zero. So they're scalar multiples. Now, the next question is what if the Wronskian is zero? Well, what can we say about this? See, here we assume that one function was a linear multiple of the other. So what if the Wronskian is zero? Well, here's a way to do this, is assume, let's say, that y2 is not the zero function. And now let's look at the derivative with respect to x of y1 divided by y2. Now, doing a little bit of calculus, it's y2 squared. Now, notice what we have. We have y1 prime, y2. It's just a simple old product rule. So that's a product rule. But notice the top. And this is not a coincidence. Notice this top here. That top looks a lot like the Wronskian, doesn't it? And in fact, it's a negative of the Wronskian. And the bottom is y2 squared. Now, if we said the Wronskian was 0, so this means that the derivative of y1 over y2 is identically the 0 function over some interval. So if you integrate both sides, or you just use the mean value theorem, what we get is y1, y2, because the interval undoes the derivative, is equal to a constant. So the functions are not linearly independent. So let's just look at those couple of examples. Remember the first one, we had y1 was, say, cosine x, y2 is sine. Well, differentiating, that's cosine x. And then we calculate the Wronskian. What we get is we get cosine squared x minus sine squared x. And that's 1. So that's certainly not 0. So these functions are linearly independent. Let's do the second one. Let's say we did the Wronskian of e to the minus 2x and e to the minus x. Well, we have e to the minus 2x here, e to the minus x, the derivative. So then the Wronskian is going to be minus e to the minus x, e to the minus 2x, minus a minus, which is a plus. So that's a negative here, minus a minus 2. And then when you add these, you get e to the minus 2x, e to the minus x, which is e to the minus 3x. And that's certainly not 0. So those functions are linearly independent also. But there are some, we can actually say a little bit more. There will be a time where you might want to compute the Wronskian of, let's say, cosine of 3x, e to the minus 4x, and let's say sine of 3x, e to the minus 4x. These will be functions that we will have of interest. And when you go to actually do the Wronskian, I'll go ahead and write the first line. So you got to take the determinant of this. But then the bottom, to calculate the derivative, we're going to need the product rule. So we have a minus 3 sine 3x e to the minus 4x. plus or minus 4 cosine 3x e to the minus 4x. And in this column, we have to do that again. 3 cosine 3x e to the minus 4x. And then it's going to be a minus 4 sine 3x e to the minus 4x. And this can be messy. To simplify, well, the next result will make this a lot easier. If the two functions that we're taking the Wronskian of are solutions to this differential equation, and we can, again, you can make this a little bit more general by allowing A1 and A2 to be continuous functions. I'll just treat them as constants, though. So if those are solutions, then the Wronskian is either always 0 or never 0. That's a key result. So if you have an addition that these two functions are solutions to this, then the Wronskian's either never 0 or always 0. The implication is we can check the Wronskian by just plugging in a single value. In the interval of validity. We don't have to treat the thing wholly as a function. So like, for example, in this mess up here, if we plug in x equals 0, so in our case, in our example, well, this is a colossal mess, but I'll just show you how this result simplifies things enormously. So let's just copy this thing down. And again, I haven't proved that these are solutions to a differential equation, but in fact they are. If I decide to say, let's just plug in x equals 0, what we get then is the determinant. Well, if x is 0, that's a 0. So we get cosine of 0 is 1. E to the minus 4x, that's just a 1. That's just a 0. Then if we plug in a 0 here, that's a 0. That's a 1. So we get a minus 4. Plugging in 0 here, we get a 0 in this term. And here we just get a positive 3. And that's easy. Okay. So that's the value of that result there. Oh gosh, I can't type. Let's say 224, set 25, 4. Okay. So now let's do a new one. So the question is why can we just check at one point? Well, let's see. So let's say that y1, whoops, I didn't want y prime, I went y1 and y2. Are solutions. And I'll go ahead and use the industrial strength version of this. I'll allow my A1 function to be, I'll allow this to be a function of x, but a constant also works. So let y1 be this solution, and let y2 be this solution. Now you might say, okay, well, so what? Well, here's what you're going to do with this. And I want to use the cut and paste so you can see what's going on real clearly. So we just going to go ahead and copy this and then paste it. And look at what we can do. Write these over each other. And my goal is I want to eliminate the y1 and y2 term by adding and subtracting the equations. So what I'm going to do to the first equation is I'm going to multiply this by y2. And I'm going to multiply the bottom equation by y1. And I'm going to subtract. Well, if you subtract the equations, look at what happens. Subtracting the equations, these two terms are exactly the same, and those are 0. And so what we get is we get y1 double prime y2 minus y2 double prime y1 plus, now here, notice the a1s here are the same. So you get a1x, then you have y2 y1 prime minus y1 y2 prime. And that has to equal 0. Now, so what you say? Well, this, of course, right here, this, as before, is a negative of the Wronskian, because the positive of the Wronskian has a positive y1. Okay? So we can rewrite this as minus a1 Wronskian. And then we have this sort of curious little thing here. Now, what is this? Well, let's take the derivative of the Wronskian with respect to x. So it's y1, y2 prime minus y1 prime, y2. And I got to use the product rule twice. Well, so using the product rule, I got the derivative of y1, y2 prime, plus y1, y2 double prime, subtract. Now I got to use your product rule again. So it's going to be y1 prime, y2 prime, plus y1 prime, y2 double prime. And notice when we do this little weird calculation here, notice this has a positive sign and that has a negative sign. So this is y2 double prime y1 minus y1 prime y2 double prime. Well, what do we have there? What we have here is the derivative, okay? So what we have right here is the derivative of the negative of the Wronskian, because this is a positive Wronskian, and it gives you the y2 double prime with a positive sign. So what we have, we can replace this thing right here with a negative of the Wronskian. So now I have the negative of the Wronskian derivative minus a Wronskian equals 0. This turns into the derivative of the Wronskian is equal to minus, in this case, I got a little bit sloppy. It isn't just an A, but it's, well, A1. So, and A1 could be a function of X if you wish. But look at this. That could be a linear first order differential equation, or it could be a separable one. So let's treat it as separable. So this is dw over w is equal to minus a1 dx by separation of variables. So now we integrate both sides. Because this is going to be the integral of minus a1 dx. And that means absolute w is log of absolute w is going to be this integral here. This doesn't have to be a constant. And then if we do a solution here by taking e of both sides, and the general thing here is you do the old trick of allowing this thing to be positive or negative, and we get this. Oh, e the log. Good gosh, that was a gaff. Get rid of that. You didn't see that. All right, so we're now down to then we just put a k, which corresponds to the c of the constant of integration, and then allowing k to be positive or negative. And so, times k. So w is either equal to 0 for all x. That's the case where k is 0. Or w is never 0 for any x, because it's an exponential if the k is not 0, right? So the bottom line is, the result of this means, so this is a conclusion. We can check linear independence by calculating the Wronskian at a point. In other words, we can just calculate the determinant of y1 of x naught, y2 of x naught. You still have to calculate the derivatives, but then after calculating the derivatives, you can plug in. And check to see if that's 0 for any interval at any point in the interval of validity. I do want to caution, though, this result only works if y1 and y2 are solutions to the same second order linear ordinary differential equation. And the classic counterexample to this is you could have y1 equal the function x to the fourth for all x. And then you can have y2 equal the function x to the fourth for x in 0 to positive infinity, and minus x to the fourth for x minus infinity to 0. And you'll notice that y1 prime 0 is 0, y2 prime of 0 is 0. So this function is, in fact, differentiable everywhere. But y1 and y2 are linearly independent on the whole interval from minus infinity to infinity. You can just check that by plugging in values. So y1 and y2 are, in fact, linearly independent. But the Wronskian of y1 and y2 at 0 is 0. So the result fails. Because, what's the conclusion? Well, these can't be solutions to the same ordinary linear second order differential equation. That's what that means. So this only works if the functions you're checking are, are solutions to the same second order ordinary linear differential equation. It doesn't work for the second part, does not work that you can just check the Wronskian by just plugging in a number. Doesn't work for all functions. So that's a little bit about it, and thanks for watching.